Yeah, thank you very much for the introduction, and thanks to the organizers for the invitation. I'm very happy to be able to speak about this recent work. So let me first mention that this is a joint work with Matteo Santacesaria, who is here in Genoa, and with Paolo Campodonico, who is a PhD student in Cambridge at the moment. So, well, Otmar has already discussed PAT in detail, so I think I'm gonna skip completely this slide and move directly to the mathematical model, which in my case is slightly different than the one discussed by Otmar because of boundary conditions. So in my situation, I consider a bounded domain where I want to do my studies, my imaging, and I take an initial pressure of the wave equation. I call it F. I think Otmar called it H. But anyway, that's exactly the same thing. And these are the initial conditions of my Cauchy problem for the wave equation. By the way, I consider C equal to 1. This is not the focus of my talk. Many things could be extended to more complicated cases, but for the moment, the speed of sound is constant. So I was saying that Otmar only had these three equations with the wave equation propagating in the whole space RD. For me, I'm gonna change the model slightly. I'm gonna put a boundary condition on the boundary of omega. This is a model which is quite studied in the literature on PAT, on photoacoustics. And the idea here is that instead of supposing that the sensors around my domain omega are just transparent to the wave propagation, I designed the sensors in such a way that they have an explicit effect on the wave propagation. In my case, I put a Dirichlet not boundary condition, but other boundary conditions can be put as well, and the following analysis would be exactly the same. So what are the measurements in this case? Of course, here I cannot measure P if P is 0 on the boundary. Physically, what could be interesting to measure is the Neumann derivative of the pressure. Of course, if here we had another kind of surface on the boundary, and so we put a Neumann condition here in the measurements, we would simply measure P. As I said, the two scenarios are very similar to each other. Okay, so I have a partial, a part of the boundary of omega that I call gamma, where I make my measurements. So I make these measurements and I measure up to time, capital T. So now my inverse problem in PAT is simply the recover of the initial condition of this wave equation from these boundary measurements given by G. And these measurements are taken on gamma and up to capital time T. So how to do that? Well, in this very simple model, the uniqueness and stability for the inverse problem are nothing but the super classical observability inequality in control theory, which reads exactly as follows. So this equation says that given a G, you find F uniquely, and the inverse map is also Lipschitz stable, which is the best you can hope for. I forgot to mention this inverse problem is linear. So, I mean, that's the simplest scenario you can have. So far, no problems. And so the question is, when do we have such an observability inequality? Well, of course, as it is reasonable, it's going to depend on gamma. So how large my part of the boundary where I measure is, and on capital T, so how long I wait for the measurements. And so there are these two conditions, for example, that guarantee one. The first condition is telling us that gamma should be large enough. And so in particular, in the case of a ball, it means that gamma should be a little bit more than half ball, half of the boundary of a sphere, and that T should be large enough. This means that you need to wait until some signal starting from inside of your domain reaches the parts of the boundary where you measure. So if these two conditions are satisfied, then you get 1. So it seems like there is nothing else to say, in that, photoacoustic is now easy. It's a linear inverse problem, super studied in the control theory literature. And so what we can do to improve things, and the idea is to let compressed sensing come into play. So before moving to compressed sensing part, let me just recall very briefly what the theory of compressed sensing is about. And the theory is, the idea is to recover a sparse quantity from few observations. So suppose you have an orthonormal basis of Cn, phi j's, in which my unknown x dagger is sparse. So it's a linear combination of few elements. You don't know which ones, but you know there's few of them. So it's only these elements in delta. And the cardinality of delta is given by S. So this is the sparsity. Then the next ingredient is the measurements. So the measurements, these are linear measurements. So by the, if you want, by the Riesz representation theorem, you can represent them by an orthonormal basis in, again, in Cn, which is given by psi k. And so these are just a scalar product between x dagger and psi k. So the idea of compressed sensing is that you don't measure all these Fourier coefficients for k between 1 and n, but you subsample them. So you measure k in a smaller set m. And so the idea is, can I still recover x dagger if I don't measure the full Fourier coefficients, generalized Fourier coefficients, if I assume sparsity? The answer is yes. And of course, you need to relate in some sense these two systems, the phi j's and the psi k's. And a way to measure this relationship is via the coherence between these two systems, which is measured by this quantity here. So I don't want to go into the details, but the typical way to recover the x dagger now is to solve this minimization problem. So these are the data, and you look for the minimum, the solution of this problem, which has the minimum L1 norm. And under some suitable assumptions on this coherence, you find that if you measure enough, and enough means up to constants and log factors, it means that the quantity of measurements should be directly proportional to the sparsity of your unknown, then x is equal to x dagger, namely the minimizer of this problem here is exactly your x dagger. And so you're in business, you will be able to solve the problem. So the idea is to extend this approach to path. So how to do subsampling in path, why is it useful, and how to do the reconstruction. So these are the questions that I want to address here. So first of all, why is it useful in path and how to do it? So far we used point-like sensors. So we suppose that we measured the boundary value of the Neumann trace of P in the whole gamma for all times t. But the point is that these are point-like sensors. We measure for all x in gamma. And the idea, and this is mainly to speed up the acquisition process and to move to dynamical path, is to go to extended sensors. And so the new measurements will be the original G with some masks. These phi L's are scalar products between the G and suitable masks that are shown in this picture here, for example. So on the left, we see the point-like sensors. So this point here is the X where I measure, and then I have to move around everywhere. On the other hand, I can consider masks. So these red guys are the phi L's, which activate only some areas of the boundary and possibly with different weights. And so this allows to speed up the acquisition process, but of course you pay a price. Instead of having G of X for all X, you have only some moments of G against these sensors phi L. And so these are the new measurements for me. And of course, this phi L will be, for instance, is in L2 of gamma. If I measure them all, so if these phi L are an orthonormal basis, of course, I'm not doing any subsampling. And so it would be equivalent to having point-like sensors. The idea is to subsample, so measure only few of these guys and see what happens. So what are the main issues of this approach? So the first one is the choices of these sensors, choices of the masks. So choices of these red patterns here. How do we choose them? And related to that is, of course, the choice of capital of the number of measurements. So I take little l in capital L, and how many of them do I need? How is this related with the sparsity on F? Okay, I knew here that in the compressed sensing theory, the number of measurements is strictly related to the sparsity of my unknown. So what happens in path? Can we reach a similar conclusion? And of course, the first thing is how to do reconstruction. There have been many works on this problem. The model here is not ours at all. However, most of these works are based are focused on the numerical side, and there are no theoretical guarantees. So there's nothing on the relationship between the sparsity on F and the types and number of measurements one should take in the spirit of a result like this one. So what can we do here? And the message of this work, I'm gonna discuss it in the next in the following slides, is the following: that we want to show that compressed sensing path reduces to compressed sensing for undersampled Fourier measurements. So in other words, from these measurements, we will transform them in undersampled Fourier measurements. And once we have these, basically we end up again in this scenario, because the scenario where the psi k's are the orthonormal basis given by Fourier, so the Fourier series is a setup that is well studied. So for example, if X dagger is sparse in wavelets, then you can do compressed sensing. If you do TV, the same thing, you can do compressed sensing. So anyway, the measurements compressed sensing, the measurements with Fourier have been studied very deeply in the compressed sensing theory. And so basically the message of this work is path can be reduced to the problem that everybody knows on compressed sensing. So how to do that? Before moving to the forward problem, let's focus on the direct problem. So how do we find P and then the Neumann value of P given the initial condition F? So the forward problem can be easily expressed with the orthonormal basis of the Dirichlet eigenfunctions of the Laplacian in omega, which are defined here. Basically, this is just an extension of the Fourier series in omega. If you're not familiar with this, just think about phi n's being the usual trigonometric polynomials. They do exactly the same thing. And then the solution to this problem here, which is our forward problem, can be expressed in this basis in this form. So this is an infinite sum. In X, you have dependence in phi n. In T, you have dependence in these cosines, which depend on the eigenvalues, lambda. And then you have these Fourier coefficients of F. Again, this is the typical exercise you do in Fourier analysis to solve the wave equation with Fourier series. Here, it's exactly the same thing in any domain. And of course, to do this, you need the Dirichlet eigenfunctions, but that's exactly the same. Okay, once we have P, it's very easy to compute the Neumann derivative. And then a posteriori also our measurements GL. So our measurements GL, I recall, these are the scalar products on the boundary between the Neumann derivative and phi L. But then this thing here is only in space because time is fixed. So here is the dependence on space is only in phi n. So the sum, these scalar products and the cosine remain unchanged. And then you just have these scalar products that change. So the Neumann derivative on P goes to the Neumann derivative of phi n, and then you do the scalar product with phi L. So this is the guy. These are our measurements where L runs along with the sensors. So these are the many sensors, and T goes from 0 to capital T. So this is just a repetition. These are my data. And from here, I want to find F. So you already see where we aim at, because here we have the Fourier coefficients of F. So the question is, how do we find them? Okay, and so I will try to convince you that it is possible to recover some of these Fourier coefficients from the GLs and then have these subsampled problem with this problem with subsample Fourier measurements. So let's fix for a moment one sensor, so L is fixed, and see what we can do about this. So with L fixed, all this thing is a constant, the thing in the square bracket. So let's call it Cn. And so our measurements are given by an infinite linear combinations of these functions cosines with different frequencies. And so the question is, from this infinite linear combination, am I able to recover the Cns? Because if the answer is yes, then I'm done. Because if I have the Cns, I obtain this guy here for all n, and then I choose the phi L so that this guy is non-zero, and I'm done. I find all the Fourier coefficients. And the answer is no, this is not possible. Why? Well, if you think about how the lambda n go as n goes to infinity, it's easy to see that they go as n to the 1 over d. So for example, in 2 dimensions, they go as the square root of n. So this means that the distance between two consecutive lambda n's goes to 0 as n goes to infinity. In other words, these cosines functions, they tend to become closer and closer to each other as n goes to infinity, which makes it impossible to recover all the Cn's from here. Okay, because somehow we lose the linear independence property. Here it's an infinite dimension, so we should move to the concept of Schauder basis. And basically what we can prove is that these cosines are not a Schauder basis, which is the analog of the basis in finite dimension for Banach spaces. So what can we do? How can we use these scalar products here? How can we use the sensors? How can we choose the sensors to make this possible? And the idea is to make many of these scalar products zero by choosing the sensors properly, and then use the theory of frames and read sequences. So before going to that, I have 2 slides that summarize what I need about read sequences. So what is a read sequence? That's an extension of the concept of orthonormal basis in a Hilbert space. And that's the following. So you take Fk, a subset of a Hilbert space H, and you consider the synthesis operator, which to each sequence of coefficients gives us the corresponding linear combinations of the Fk. And of course, if the Fk is an orthonormal basis, this map here is an isometry, and so everything is very nice. However, in this case, we don't require that this is an isometry. We only require this map to be bounded, namely, it's always possible given a set of coefficients to find the corresponding linear combinations. But the 2 important properties that we need are the fact that this map has to be injective with bounded inverse. So if we write these 3 conditions with inequalities, we get this. And the fact that this map is injective with bounded inverse is represented by this inequality here. And if you look at it, you see that this inequality is telling us that the knowledge of this linear combination gives us uniquely the CKs, because if this is 0, then the CKs are all 0. And so the problem is injective, but not only that, it gives us also bounded inverse, and the norm of the inverse is determined by A. So the bigger A, the better for us. Just as a reminder, maybe some of you are familiar with the concept of frame. These are very connected concepts, but somehow the idea is that with frames, the focus is on F, is in the Hilbert space. So the focus is on representing all functions, all vectors in the Hilbert space via our FKs. Here, on the other hand, the focus is on the coefficients FCK. So here, I don't care that this guy here may represent all objects in the Hilbert space. However, I care about the fact that this representation has to be unique, that from the linear combination, I can find the coefficients. Okay, and then how can this be made more explicit in the concept of exponentials? So in the concept of Fourier series, of course, Fourier series is a very simple example of orthonormal basis of L2 of 0t when the lambda k's are uniformly spaced. However, in our case, the lambda k's will be related to eigenvalues of a differential operator, so we cannot expect them to be exactly uniformly spaced. And so there will be a sequence, an increasing sequence of non-negative numbers. And so when is this guy a Riesz sequence in L2? So many of these results can be found in this book on non-harmonic Fourier series. I'm just citing you one of these results, which is telling us that if the minimum distance between the frequencies is bounded by below by a constant that depends on t, so of course the larger t is, then the smaller this minimum distance can be, as it is usually with Fourier series. Then if you have this, then this family is a Riesz sequence in L2 of 0t, so we are okay. And the lower bound is given explicitly by basically gamma and capital T. Okay, so basically as soon as these frequencies the distance is not too close, then we are okay. This is a Riesz sequence. That's exactly what didn't happen before, because this distance went to 0 as k went to infinity. And so the gamma before was 0. So how can we use this result here in path? So as we said, we cannot use it directly here because this distance in the gamma in this case is 0. We need to kill some of these coefficients. And now we move to consider some examples, because we were not able to do this in full generality. I will come back to this at the end, to what to do in the general case. However, the example I'm going to consider, these are simple geometries which are very popular in the application. So it's not, it's still relevant for the applications, and also as a motivating idea for possible further investigations. So the first example is the disk. So we suppose we are in the 2D disk in 2 dimensions, and we measure on the whole boundary. So the system of eigenfunctions and eigenvalues is this one, where we see the Bessel functions and their zeros. So the capital J's are the Bessel functions, and the little j's are the zeros of the Bessel functions. So you see that this eigenfunction here depends on the angular on the radius rho. Here we are in polar coordinates. The radius is rho, and on the angular variable we just have the usual Fourier functions, the trigonometric polynomials. So what masks should we choose in this case when a simple choice is given by e to the il theta? So we consider this simple orthonormal basis of the boundary of the disk, and let's see what these masks give us. So here is the only calculation that I'm gonna show in this talk. So basically the GLs, this is the expression we had before. Now, if you have to do the Neumann derivative of the phi n, this corresponds to doing the derivative with respect to rho. But if you differentiate with respect to rho, you will get a constant here, some constant here, and the e to the I n theta is untouched. And so what you get is a constant times e to the I n theta, and here you have again phi L. However, since phi L is e to the I L theta, the scalar product of these two guys gives us the Dirac delta with n and L. And so this does exactly what I said at the beginning. Many of these scalar products become 0. And so we can remove one of this sum, because we had two sums here. One of them is removed, and we end up only with one sum because n is equal to L. And so that's the final expression we reach. And at this point, you see the advantage is that if at the beginning we summed over n and k, so the corresponding lambdas here, the corresponding eigenvalues, we had them all over n and k. Now the little l is fixed by the measurement that I'm making. And so here the only variable is k. So why is this useful? Well, because at this point, these are the measurements, we can use the result on Riesz sequences that we had before. We know that if these j's, the distance is large enough, then this is a Riesz sequence and we can recover all these coefficients. And then I don't do the calculations here, but we just need to go and look at the zeros of the Bessel functions. You compute them, you calculate the distance, and you find that indeed this condition here is satisfied, as long as t, for example, is bigger than 1.01. So if you have this, then these cosines actually give us a Riesz sequence in the space, and the lower bound A is independent of L. So the same time capital T works for all sensors L, and then you can recover these coefficients by inverting basically this operator here. We know that the inverse is bounded, so it's easy to do that A is independent of L, and the explicit expression is this one and depends on the frame operator associated to the Riesz sequence, to this Riesz sequence here, which depends on the synthesis operator, which I discussed before. So this is the 2D disk. So what can we say in terms of compressed sensing? Well, it says that from these measurements here, these were the path measurements, I can recover by using Riesz sequences these Fourier coefficients of f. And so you see that this is what I said at the beginning, that compressed sensing path can be reduced to compressed sensing for undersampled Fourier measurements. And these are undersampled Fourier measurements because I'm not measuring all Fourier coefficients, I'm measuring a subset of all possible Fourier coefficients. So this is a typical compressed sensing problem. The only difference is that we have a structured subsampling pattern. So this is not a completely random subsampling pattern in the frequency space, but it's got a structure which is saying that basically the only subsampling you do it in L. There's no subsampling in K. So for each mass, you measure all K. So we have a structured subsampling pattern. These have been studied quite a lot in the compressed sensing literature. Okay, now let's move to the other example, which is the square. So what happens with the 2D square or with a rectangle? It would be exactly the same thing. And this was studied in this paper of a few years ago. And basically the method that I discussed here, first of all, it takes into account compressed sensing, and basically it's a completely different approach based on Riesz sequences. These authors didn't use Riesz sequences to do the inversion. So let's see. In the square, the situation is very much is exactly the situation that you get with Fourier series, because the eigenfunctions and eigenvalues, these are exactly the objects that you find with classical Fourier series. And therefore, suppose we measure on only one side. So this is the right side, and we measure only on one side, and the masks that we choose are simple trigonometric functions here. These are sines with different frequencies. And then basically you do the calculation that I did before with the disk. You do it for the square, and you use the fact that these functions, these sines, are orthogonal to each other. And so what you end up with are measurements that do not have a double series and K, but the sum with K is blocked, and K basically is equal to L, the sensor that you are using. And so now these are the measurements. And so from here, you just need to look at this lambda NL, and it's easy to see that you can again use the theory of Riesz sequences and obtain that this guy here is indeed a Riesz sequence for every L. However, a slightly annoying situation appears, because here, so let me show you this image. These are this sequence here, lambda NL with L fixed. Okay, this guy here with L fixed. And so here is N. And so you see that you have a nice separation, and so you can do the inversion. However, when you increase L, what happens? Well, you see that the minimum separation becomes smaller and smaller, especially here. Here, the situation is okay, but here it becomes smaller and smaller when you increase L. And so we expect that when we increase L, this minimum distance goes to 0, and therefore the frame operator, the inverse of the frame operator, its norm goes to infinity, and so the recovery of these coefficients become more and more unstable as L goes to infinity. So basically, if you fix a noise level, you can hope for the recovery of up to a certain threshold given by L, which depends on capital T. Okay, so what are the implications in compressed sensing? Well, these were the path measurements. By doing this inversion using read sequences, we can measure the Fourier coefficients of F. Here I'm using the standard hat with the Fourier series because these are basically exactly Fourier series. And you see, these are, again, subsample Fourier measurements because you don't measure all frequencies, you measure all frequencies in N, but not in L. And so basically, this is a picture. Instead of measuring all dots, in the variable L, you have to stop at a certain point because of this phenomenon, because at some point, these guys here become too close to each other. And then from 1 to L bar, you do your subsampling. And so that's the typical subsampling pattern you get for these kind of problems. Now, here so far we measure only on one side. What happens if we decide to measure on two sides? Well, let's go back. So let me just recall why things got bad. Well, we had to stop because as L goes to infinity, this minimum distance between the eigenvalues went to 0 because between the frequencies of the cosines. And that's what is explained here exactly. However, as you see very well in this picture, the bad behavior is only at the beginning. For high frequencies, things seem to be fine. And if I underline here the point L, you see that after this blue point, things are always okay. Before the blue point, I have the distances that are too small. In other words, if we put this in formula, we get that if we do at L fixed the infimum over, not over all N, but only over N bigger than L, then this infimum is bounded below by a positive constant, which is an absolute positive constant. And so this suggests that if we measure only those frequencies for which N is bigger than L, so basically in this half plane here, in this half space here, then we can go up to plus infinity. So we don't have to stop at L bar, we can go up as much as we like. But then this suggests the following, that if we can measure half of this by measuring on one side, then if we measure on the top side, then we are able to recover all the other half of the Fourier coefficients. And then basically these lines represent the subsampling. So here we do subsampling in this direction, and here we do subsampling in the other direction. If we had full sampling, then we would be able to recover all Fourier coefficients. Well, here we are doing subsampling on the masks phi L given by the signs. Okay, so this concludes the analysis. Let me just conclude by showing some simulations. So first of all, let's start with some reconstructions without subsampling. So we suppose here we do only the square, and we suppose here to have the full data, so no subsampling. So here is the case with two sides. Well, it's not a surprise if we have two sides with no subsampling. We are in this case here with no empty lines. And so of course the reconstruction is perfect. However, what happens if we measure only on the right or on the top side? Well, it means that we are in this scenario here, where we measure only these frequencies here, again, without subsampling. And that's what you get. And these are the typical artifacts that we would observe with limited angle tomography. Okay, depending on the side where we measure, you see the typical artifacts and the typical unseen, invisible singularities that can be, of course, explained also with microlocal analysis. The explanation here, however, is purely on the Fourier analysis side, on the signal processing side. Simply, we cannot measure high frequencies in one direction, only in the other direction. And so basically, that's what you get, these different explanations. These different figures depend exactly on the side. Next, let's see the influence of t, of the time capital T, so the measuring time. As we saw here, the measuring time basically is telling us how small this minimum distance can be. The larger capital T is, the smaller this minimum distance can be, and so the larger the parameter L can be, the larger L can be chosen. So if we are here, we see that for small capital T, then high frequencies are completely lost. For a larger capital T, you see that still we can improve the reconstruction even with only one side. Measurements are done only with one side, and so basically this is the phenomenon that is explained here. The larger capital T is, the larger L bar can be, and so you push this up, and so of course you recover more frequencies here. Okay, and then finally, this is the slide with the compressed sensing result. And so the bottom slide is the classical compressed sensing. So here is the subsampling pattern. So the black dots means we don't measure, and the white dots means we are measuring there. So here we are choosing 8% of the Fourier coefficients. And this is the minimum energy solution. So basically we put to 0 the black Fourier coefficients, and we do the inversion with the inverse Fourier transform, and that's what you get. If you do TV, that's of course the exact solution. So this is basically the usual very connected to the usual simulations that you do in compressed sensing to show how powerful this method is. And this is what happens with PAT. So with PAT, we saw that the difference between classical compressed sensing lies in the type of subsampling pattern that we use. Instead of having a random subsampling pattern, we have a structured subsampling pattern. So this structure is given here. These structures here. Again, the white lines correspond to measuring this sensor, and the black lines means I don't use that sensors. And here we use a bit more than 13, if I remember well, percent of the masks. So instead of using all Fourier coefficients, we use only 13% of the masks, of the sensors on the boundaries. And again, this is the minimum energy solution. So putting to 0 the Fourier coefficients that we don't have. And this is the minimum TV solution. So we see that basically the only aim of this slide is illustrating the effect of this subsampling pattern, because of course, if the subsampling pattern was completely random, then we would have ended up exactly in the classical scenario of compressed sensing. Here, the subsampling pattern is structured, but you see that up to a slight, we lose a little bit in the subsampling pattern, but still the recovery is still pretty good. Okay, let me conclude. As we said, compressed sensing pattern has been studied a lot and used also in practice, but without the full theoretical support in the spirit of the compressed sensing theory. And what we showed here is that by using the theory of non-harmonic Fourier series, it is possible to show that compressed sensing path can be reduced to a problem of compressed sensing for undersampled Fourier measurements with a structured subsampling pattern. In the paper, you also find extensions to the 3D case. These are basically straightforward, and also to the free space model for the wave propagation. Here, I illustrated the bounded domain model because I like it more. I think it's more fun from the mathematical point of view, but similar considerations, not all of them, but many of them can be also done in the free space model. And what future directions do we have? Well, first of all, a rigorous proof of the square with two sides. Here, I was a little bit sloppy by showing that, oh yes, if this infimum is bounded by this constant, then you can recover stably this half plane. Actually, it is not, well, we will not be able to prove this. Of course, the numerics show that this is true, but the proof so far, we will not be able to do the proof here. The second interesting approach is to study the problem for general domains. This approach aims at making those scalar products exactly zero to simplify a lot the series. However, it is possible that other approaches can be done for general domains. We haven't investigated it yet. And then a more thorough study of compressed sensing with those kinds of structured subsampling pattern. There is something in the paper, but it's not fully addressed, this issue. Okay, this is the end of my talk. Thanks a lot for the attention.